Good morning and welcome to everybody to the second webinar of Sunrise project. This webinar will be about the sensors for automatic sorting processes. The first speech, that is an introduction on sensors, is given by Dr. Maxime Gouc from IREC, that is the Catalonian Institute for Energy Research, where he works as a consolidated postdoctoral researcher at the Solar Energy Materials and Solar Cells Group, coordinating the research line on advanced combinational characterization of materials and devices. Maxime holds a PhD in physics, and his research interests are centered on two main topics: the fundamental characterization of semiconductor materials, with a focus on thin film for photovoltaics, by applying spectroscopic, electrical, and optoelectronic techniques, and the development of physical-chemical characterization methodologies for semiconductor materials and devices, and their application to the inline monitoring and control of industrial processes. So, Maxime, please, the floor is yours.
Thank you, Alessandro, for the kind presentation. So, yeah, sorry. So, do you see my screen, I hope?
Yes.
Okay, so I move to the presentation mode. So, good morning, everybody. As Alessandro already said, my talk will be about the introduction on sensors, on what is sensor in generally means, and how we can develop a sensor, and how we can what are the main step in development of a sensor. So, first of all, I would like to say some words about our institute, about our group. So, IREC is a relatively young research institute that is focused on development of new disruptive energy solutions and bring them to the society. So, we are a fast-growing institute, and we are increasing a lot the personnel, and of course, our participation in the European projects and in the different European level. And as a part of solar, and so as a part of institute, we are presenting Solar Energy Materials and Systems Group. So, sorry, there is something more. So, solar energy, follows from the title of the group. Our main topic and our main research line is related to the development of the materials related to the photovoltaic technologies. We are developing new materials, new concepts, and we are also trying to transfer our technologies to the implementation in different industrial lines. And the second part of the group, or the second research line of the group, this is where appears the Sunrise project, is related to the characterization and implementation of our knowledge of characterization for the development of new methodologies for industrial control and for industrial control of different production processes, for classification of the materials. And here where comes Sunrise, that we are, with all our knowledge about the material science and different methodologies, we propose the method for the characterization of laminated glasses. So, first of all, I would start more or less in general my presentation on saying what means for us a sensor. So really, a sensor is different products which are really around us every day. It can be some temperature sensor, or motion sensor, or video sensor. It can be some more advanced sensors that we are using in our labs, or the sensors that we are using in really industrial processes and production. So the type of sensors and the variation of sensors is really, really high. So we can have a really big difference and big difference in the type of the sensors. But in any case, we can define some more or less strict way of, or strict elements or components of the sensors. So this can be, this is here you see this can be control unit, output, encapsulation, integration, data processing, signal detector, some excitation elements. Some of these components can be not necessarily are present in all of the sensors. Some of them are really present. So speaking about the proposed examples, we can say that, okay, here in this light sensor we have an output that shows us information about the parameters that we are measuring. There is a data processing and control unit that allows us to manipulate the sensor properties in different ways. There is a signal detector which directly detects the signal or properties that we are measuring by the sensor, and this black yellow box can be, say, as a encapsulation of the sensor. So you see, in most of the cases we can define all these main components of a sensor independently of the function of the sensor. So what information can provide us a sensor in industrial cases usually? So a sensor can evaluate the quality of a raw material, so the material that is entering the industrial process. Then we can sort the material or waste of products that is developed during the industrial process, or we can introduce sensors at different production steps and control the quality of these production steps, or what's happening, or if there is some deviations in these production steps. So finally, on how we can integrate, or what is the ways of integration of a sensor in the production line. So there is two main ways: it's in situ or ex situ. So in situ means that we are integrating sensor directly in the production process. So during the process, we are checking the quality of the product. And ex situ is what we are measuring afterwards, after we finish some step or the full production process, or afterwards. So and ex situ can be also different ways. So we can have the inline monitoring, which means that we monitor all the all the products that we are making during our production, or it can be online. So which means that just a part of the production products are evaluated, or offline. In the offline case, we are just taking some representative sample of the production process and go to the lab and measure it outside of the production process. And in this case, the evaluated sample is never coming back to the production process, which is different from the online, for instance. And how we afterwards can integrate sensor in the way of in the more general way, on different steps, on different processes. So if we consider some, for instance, PV module recycling flow, then there is two different ways on where we can integrate sensors that checking the differentiates different type of photovoltaic modules. So the first way we can integrate it in the some warehouse where we are just collecting different types of PV modules from different plants, and after classification of the PV modules, we send them directly to the specific companies that can recycle this specific type of PV modules, or we can directly integrate the classification sensor, in this case in the recycling plant. So it means that all different types of PV modules are coming to this recycling plant, but the recycling company selects just that type of the modules that they can recycle and they can reuse afterwards. So there is a different way of integrating the sensors. And okay, what can be the development steps for a sensor? This, of course, a lot depends on the type of the sensor and the type of technology we are using. But in any case, we can define more or less some specific or some general ways in development of a sensor. So there is main two branch in the development line that are related to the development of hardware part and software part. But in any case, all this starts from development of materials. All this starts from the characterization of the materials or of the devices that we are going to analyze by a sensor. So we start with the characterization, then we have some development of the standalone sensors, and we also have the development of methodologies on how to characterize our materials or our devices, and finally we end up with some final sensor that allows us to reach the goal and to understand or implement this sensor in the production line or in the recycling plant. So going now to the Sunrise project, as many of you know, and if you know somebody doesn't know, that Sunrise project, the main goal of the project is to develop some specific mechanochemical treatments for the laminated glass waste, to recycle the laminated glass waste, and for instance recycle the PVB material that is inside the laminated glass. And this is always based on this treatment will be based on the application of the advanced sorting platform that is based on the multisensor tool. So we can define two main sub-objectives of the project. So first of all is, of course, the mechanochemical treatments of the PVB byproduct that is already was discussed in the previous webinar of the Sunrise project. But there is also this part of development of advanced sorting platform, and which is based on the multisensor tool. So this is what we are going to discuss today, and this is what I'm going to show you our latest results in this development part. So what is a advanced sorting platform? So this is quite easy. So it's some platform that takes a waste laminated glass, analyze it, and classify it by different criteria that are defined by the project and are useful to the recycling afterwards, this laminated glass. So, and here this is a part where multisensor tool appears, and this multisensor tool is based on the spectroscopic techniques. So why we are using spectroscopic technique, or what is a spectroscopic technique? First of all, so this is a character materials or device characterization technique that is based on the analysis of the light. So first of all, we have some excitation of the light signal, can be excitation by light or electrical excitation of some chemical excitation, whatever. And then we analyze the light after excitation or after interaction with the material. And there are a lot of different type of spectroscopic techniques. Here I just show some of them that we are using in different technologies. And the main advantages of the spectroscopic techniques and their good use in the sensoring and the development of sensor is that they are non-destructive. They don't usually require any specific sample preparation. They are relatively fast, so we can quite easy scalable them and integrate in the production line or in the classification line. So what information we can get from a spectroscopic technique? It's of course depends a lot on the specific technique, but as you see, there is a quite wide range of the information we can obtain from different techniques. So we can know about the chemical composition or chemical bonds that are inside our material, some optical properties, transmittance or reflectance or coloring, haze. And there is some more specific information about the material crystalline structure or electrical properties or some interconnection defects. So a lot of information that we can gain from analysis of the spectroscopic from application of the spectroscopic technique. So combining different spectroscopic techniques, we can really get a full picture about the material's properties, and this will allow us to increase a lot the sensitivity of our sensor. So this is why we are always speaking about the multisensor tool, and when we are showing a multisensor tool, this is usually a combination of different sensors. So what can be a spectroscopic sensor, or what parts can be inside the spectroscopic sensor? In this case, it's some light source unit. So there is a different type of light sources that we can use in our spectroscopic sensors. Can be just a broad white light or some specific very high quality laser light with a narrow emission band. So this light this light reach the sensing unit. So this is which we also in a lot of cases we are calling these probe heads, or the sensor probe heads, and these are the parts that require more efforts in the development of the sensors, as they are directly interacting with our material with a laminated glass in the case of Sunrise project, and these are the most maybe complicated part to be developed. And after interaction of the light with our sample, it reached some detectors or monochromator unit, where we have also different configuration depending on the technology the technique we are using for the sensor, and all is controlled, of course, by some control and data processing unit that allows us to manipulate with different parts of the sensor and control them, and of course collect the information and treat it in the way that allows to provide us useful information about our material, about our sample. So having in mind all this, okay, the development of the Sunrise sensors, we of course started with advanced characterization, which was done with the help of different partners of the project, and different techniques were used in this case and for different samples, and these samples created a first database about the reference samples, that we know a lot about these sensors and we understand what sensors about. So finally, in a part this advanced characterization technique, we also use some techniques that we were planning to apply in the sensors, or different spectroscopic techniques that we were planning to apply in the sensors, and all this information created our database about the reference samples and about all the information that we know about the reference samples. Afterwards, we selected some specific features in different spectroscopic, in different spectra that we measured from these reference samples, and based on this, or in some cases we didn't found this feature, so we just delete these techniques from the further considerations. And having in this information, we created the first version of methodologies that allowed us to classify the laminated glasses, or the laminated glass wastes. And from the hardware part, so before I was speaking about the software part, and from hardware part, we was, as I said, a lot focused on the development of the probe heads for different sensors. And here you see some examples that were developed by IREC and by other partners of the Sunrise project. And as I said, of course, the development of the probe heads was quite important part of the project, but of course, selecting an optimal components for other units of the sensor, like light sources and optomechanical and optical elements, some detectors, spectrometers. This was also quite important part. So we were checking different possibilities, and finally selected the best of them. And this allowed us to develop a standalone sensors that you can see here, some photo of the real sensors or laboratory sensors that we was developing, and we're already testing them by measuring different properties or different spectra, and classifying the reference samples. So we still was working with the same reference samples. So this lead us to some materials device characterization with a real sensor that developed inside the project. And now we are working in the integration step or integration task of the sensors. And here you can see some design of the possible integration of the different sensors. So this is a final task that we already finished in the Sunrise project, and now we are working in implementing this this design in the real life. So with this, I would like to end up my talk, to send all solar energy materials and system group that are working in quite different topics, and thank you for your attention.
Thank you, Maxime, for the very interesting and clear introduction about sensors. So now it's my pleasure to introduce the second speaker of today, that is Anna Lara from IDENER, who is going to speak about the development of a computational decision support tool. Anna is a process engineer working at IDENER since 2019. She is responsible for the project management of several European projects related to modeling and optimization activities. In this position, she helps industrial partners and universities to optimize and digitalize their chemical processes to save money and time. In the following presentation, she will show the tool that IDENER has developed to digitalize and model the Sunrise project. So please, Anna, the floor is yours.
Okay, well, hello everyone. Thank you very much, Alessandro, for the introduction. Okay, I think, can you see my screen?
Yes.
Okay, perfect. Well, as Alessandro said, I'm going to talk about the work that IDENER is developing in the Sunrise process by creating a computational decision support tool which can digitalize the process that we are studying in the project. Okay. So, well, as an introduction, this is this first slide briefly describes how the tool architecture of this computational tool has been developed. Okay, it is remarkable that this tool is divided in two different parts. Okay, the first one is the development of the mathematical model that we are developing in order to describe the Sunrise process performance and to develop its optimization. Okay, because we have developed several mathematical models in order to describe each unit operation of the process. And for that purpose, we have used the software Python by developing some algorithms and using the object-oriented programming. Okay, and then the second part of the tool is a program using .NET. Okay, in the Blazor app, and this includes like the more visual part of the tool. Okay, this is like the user interface where the input and the output variables of the process are shown. Also some diagram of picture of the process that we have included in the tool, and also the result that the tool provides will be shown. Okay, so by combining these two different parts, the Python and the Blazor app, we can obtain this computational decision support tool. Okay, so during the following slides, I'm going to show you how this tool of the Sunrise process look like and the different functionality that we have included. Okay. Well, so this is like the home window of the platform where we can log in by user a specific user. Okay, this is not an open source tool because it contains some confidential information of the process. So that's why at the moment we have included this specific user to enter. Okay, and well, once we have logged in, this is the web interface where we are directed to. Okay, well, here the user can see a general diagram of the process, including well, the different equipment, process stream, also the raw material that is fed to the process, and the output stream we obtain. Okay, and well, in this case, the process is divided into three different parts. Okay, which are the multisensor that Maxime has explained. Also, we have the mechanical treatment and the chemical treatment. Okay, and well. Here in this diagram, in these symbols, you can see we have included some pop-ups where the user can find a general description of each part of the diagram, okay, of the different equipment and the process stream in order to have a more detailed explanation of the process. And well, here in the left part of the interface, we have like a lateral menu where we have included the different section of the tool. Okay, and well, as you can see, now we are on the first window, which is the home window, explaining an overview of the project. And now we are going to move to the simulation window. Okay, which looks like this. Here, well, the user can see again the process overview, the diagram. Also, we show some information about the process, and we have the input variables part, which is like the core of this simulation part. Okay, because in this window the idea is that the user can introduce the desired values of the input variables of the process, and with this information, the tool will solve the different mathematical model that we have programmed in Python, and will provide the user with the mass balance result that we obtain by running this simulation. Okay, so for that purpose, we have divided the input variables in the three process category. Okay, the sorting, the chemical, and the mechanical treatment. And when the user click, for example, on the sorting part, okay, this is what we will see. Okay, the tool will show us all the input variables that are associated with this sorting unit. Okay. Well, here we don't have include the real name of the variables in order to protect the project confidentiality. Okay, but the idea is that you will see all the input variable together with a generic description of this variable to better identify it in the process. Okay, so well, here the user must fill in all these values of the variables. Okay, and once it is complete, the tool will solve the mathematical models and will show us the result. Okay, in this case, the result will be shown in different formats. Okay, we will have like a picture format and also a table. Okay, here the idea is that in the y-axis we will have the value of the desired output variable, and in the x-axis we will have the value associated to each string of the process. Okay, but well, of course, the user will also have the possibility to downloading the complete mass balance table result of all the system in an Excel or in a PDF format, okay, in order to see like a more global overview of the result of the simulation, okay? And well, that would be all about the simulation section of our tool. And now we will move to the next one, which is here we have the admin window. Okay, this is quite simple, but we think it could be very useful for the user, okay? Here, the idea that if the user finds it necessary for an easier understanding of the interface and the process, it will be possible to change the information of the different pop-ups that we have included along the complete interface, okay? Like, for example, we can change the process description or adding some details that we want. Also, the description of the equipment or the stream that I show in the home window. And we will also can change the information of the variables in the simulation window, okay? This is quite useful because sometimes we can have a lot of variables, and with the name and our description, it can be difficult to identify. So if you can put the information that you want, it will let you to save time, okay? So this is easier. You only have to click on the edit button, and the tool will let you to write what you want in this pop-up, okay? And well, finally, as you can see in the lateral menu, our last part will be the optimization part, okay? But I cannot show it to you yet, okay, because it is not finished. It is we are working on the development, but the idea would be to provide the user with more detailed information about the calculation, okay? For example, based on our simulation tool, the user can develop a sensitivity analysis in order to better study a more interesting variable if it is necessary. Or the tool also will provide you the process optimization with economic criteria, okay, providing the more optimum values of the variables to increase the profitability, okay? But as I said, this is like the future work, so we are still working about it, okay? So, well, that would be all about my presentation. Thank you all of you for your attention, and well, here you have my contact data in case you want to contact me or or at the end of the webinar, you can ask any comment or any question that you consider.
Thank you very much, Anna, for very interesting explanation. So the last speaker of today, and then there will be room for some discussion if there are questions from the audience. Last speaker is Juan Manuel Rodriguez from LENZ Instruments, and he will speak about the integration of advanced sensors into waste sorting lines. Juan holds a master's degree in telecommunication and electronics engineering at the Polytechnical University of Catalonia. He is responsible for the company engineering department, and he has over 20 years of experience in the development and the commercialization of technological products and services for different industrial sectors, including also the food industry. His main research interest is the application of non-destructive and non-contact inspection technologies for industrial applications, including magnetic induction and optical spectroscopy. So Juan, the floor is yours.
Okay, thank you very much, Alessandro. Good morning to the audience. I'm going to try to share my presentation. One moment. Okay, I hope you can see it.
Yes.
Okay. Well, as Alessandro says, my talk is about sensors for automatic processes, and more specifically, the integration of advanced sensors into the sorting lines. My presentation is divided in three parts. We are going to talk about industrial requirements, sensor technologies, and finally, we are going to show you some case studies in which we are working. Well, concerning industrial requirements, of course, there are some key issues when upscaling sorting technology from the lab to the industry. Basically, when you start working in a non-destructive or inspection technology, basically you focus very much on the accuracy of the method and of course the throughput, the analysis time, the sorting time or separation time. These at these stages are probably the more important key issues. Once you have achieved this, once you have succeed, then other industrial requirements becomes important. Specifically, when you want to go to the industrial process, to the practice, then the first question is how reliable is your product? And then reliability is very important because your system is going to work in a harsh environment that more probably will be there will be mechanical vibrations, dust, electromagnetic interference. So your sensors must be very robust to perform well in an industrial environment. There are also other key issues related with the integration, space constraints, electromechanical, industrial communications, to send all the data in time. Also, of course, you have to, depending on the technology you are using, you have to comply with normatives and directives, especially, for instance, when you are using a high-power laser beam or X-ray source, you have to be sure that your system is safe for the workers that might be surrounding the installation. After that, there are other questions that need to be addressed, and probably more related with the economical point of view. For instance, the maintenance. If your system requires a lot of maintenance, is cheap, is expensive, how often I have to replace, for instance, a laser source or a X-ray lamp. there is important questions that the customer will ask. So this has to be also taken into account. Imagine that you are using a kind of laser that has to be replaced every 3 weeks. So this is probably not affordable for the company, but well, this depending on the application, maintenance will be important. Of course, there is the cost issues that we can talk about initial investment or capital investment. How much is the cost of this sorting installation? This is one thing. And also the operational cost. How much is will cost me to run the installation in the time? So at the end, for every application, there is you have to perform a business case analysis to see if the system that you have developed is really worth it or not. It's not the same to sort plastics that compared to sorting, for instance, metallic scrap, which probably has a higher cost, or if you're trying to sort demolition waste, which is cost nothing. So, but not only the economical point is important, because maybe there are cases in which the important thing is the recycling, and maybe there is a law that obliges the industrial partner to recover this material, and it's not only an economic matter, but it's a matter also of the environmental issues. So all this has to be into account in a business case analysis, and normally this last part comes when you have something working at the lab. Well, concerning sensor technologies, we're talking about advanced sensors, and this has to provide an advantage in terms of ability to, for instance, ability to measure a new target parameter that other sensors in the market cannot measure, or even the combination of multiple target parameters in order to have enough data to perform a specific result, or to be able to effectively sorting your material. Of course, we can talk about improved accuracy, or sensors that has a wider spectral range that allows you to determine things that with other kind of sensors you cannot do. Or can be sensors that can perform analysis at very high speed. Imagine you have to process tons of products tons of material per hour. A sensor that has not the required speed will not be useful for the application. So this is something that an advanced sensor can provide. We can also talk about the configuration of this sensor. Maybe the sensor can provide a non-destructive analysis, or provides a better spatial resolution, or is a sensor that can be used to do remote sensing, and this is something that not other sensors can do. So this is all these characteristics that the advanced sensors can provide. Also, improved data analysis capability, as more of the applications, major part of the applications will require inline capability or inline sorting. About these technologies, we are talking about, in this case, of sensor based on spectroscopic technologies. For instance, you have the vibrational spectroscopy. To mention some of them, we have near spectroscopy, Raman spectroscopy, Fourier transform, infrared. We also have in another wavelength optical spectroscopy from the ultraviolet to visible spectrum, photoluminescence, elemental techniques, elemental analysis techniques like laser-induced breakdown spectroscopy, or X-ray fluorescence. And finally, we have also hyperspectral imaging sensors. Well, all these technologies can be used for sorting of different materials, and I'm going to present some case studies, specifically 3 case studies. The first one is related to this Sunrise project, in which, as you know, we want to classify the polyvinyl butyral interlayer films in laminated glasses. As you may know, these interlayer films are used to avoid the glass to be broken in big pieces, because this is dangerous for the people. So these interlayer films allows to keep all the glass when it's broken in small pieces that are safe for any person that can be nearby. So which technologies we are using? Basically, we are, as Maxime says before, a multi-sensor platform which combines near spectroscopy, Raman, colorimetry, and light scattering to identify different optical properties or quality of the material and its chemical composition. So at the end of the year, there is a significant amount of these laminated glasses that needs to be recovered. So we are trying to provide a tool to facilitate this recycling, or at least to recycling these laminated or these interlayer films properly. So trying to separate this laminated glass in different qualities, so you can separate the interlayers to be reused again, and the quality groups are important for this process. So basically, we are working with 50 by 50 centimeter panels that are manually fed into the platform, and at this moment we are working at a speed of 2 panels per minute, giving a total of 120 panels per hour. So you are going to see now a representation or an infography of the system that we have already developed. The platform is divided in 3 stages. The first one is performing colorimetry of the panel and also the elastic scattering. Second stage is making a near spectroscopy analysis of the glass. And the third stage is the Raman spectroscopy head. And after this analysis, using these models, we can separate the glass in different quality groups. Okay, second case study is about sorting of aluminium scrap into different alloys, into different families. Basically, this stream is coming from the end-of-life vehicles. And basically, we are using also a multi-sensor platform, but in a different way. We are using eddy current sensor matrix and LIPS technology. And the eddy current sensor, in this case, is not to extract information from the material, but it is used for to know what is the location of every single piece onto the conveyor belt, because this is a conveyor belt of 120 centimeters wide, mounting 6 LIPS head sensors. Every head is covering a range of 20 centimeters in the line. So basically what we need is to know in which position is the scrap that will pass through the or below the LIPS head. So we need to know exactly the position and a specific moment to point the laser in this 20 centimeter range and fire the laser to impact the fragment. So when the laser impacts the fragment, the metallic fragment, it generates a plasma or a spark that this emission light is collected and goes to a spectrometer, and analyzing this spectrum, we can do an elemental composition. Basically, we can determine the amount of the content of the silicon and the magnesium present in the scrap metal, and this is related to the family of the aluminum. Of course, these leap sensors can be also adapted to measure other metals, like, for instance, brass, copper, stainless steel. In this particular case, is configured to the sorting aluminum families, and all this information that is collected by the spectrometer has to be analyzed very fast, because at the end of the output of the conveyor of the line, we have to eject every single piece into. In this case, we separate in 3 families, in three streams. So basically, we have 3 array of ejectors. One is blowing up, a second ejector, array of ejector is blowing down, and the third one is using gravity force just to leave the metallic scrap to be in the third stream. So basically, the throughput or the processing speed that we have achieved with this system is 1 ton per hour, more or less, using a speed of 1 meter per second. So all the things, all the parts of the modules composed by this platform has to be very well synchronized and has to operate at very high speed in order to make an effective sorting of the material. Now, where you are going to see a real representation or a real demonstration of this working. Yeah. In the first stage, we have a vibrator which spread all the scrap metals onto a conveyor belt, and then the metallic detector gives the information to the leap sensor, and then we are, as you can see in the image, this is a very slow image. Where the laser is fire all the metallic single metallic scraps, and this is the last output stage. We were separating in 3 parts. Okay, this is it was recorded with a high-speed camera, because it's so fast that you cannot see with you cannot follow with your eye. The last case study is related with the separation of construction and demolition waste. At the moment, is is a process in which the separation of this kind of waste in economical terms is not very attractive, let's say. But it's important from the environmental point of view, because, for instance, the production of concrete is very energy intensive. So it might happen that when the technology is ready, will be a law that obliges all in the future, that obliges all the industrial stakeholders involved in this sector to recover, to separate the concrete, to reuse it, because the amount of energy used is very high. So this is an environmental problem. So we are working in providing this technology for the sector. In this case, we are using hyperspectral near imaging that is useful because we can have information about the chemical composition of the waste. And basically what we are doing here is to separate the concrete from the ceramics. In this particular case, we are separating concrete from bricks from gypsum. So we are separating all the stream in 3 different materials. We are using air ejector matrix like in the previous case. And in this case, we are, due to the kind of technology we are using imaging, so we can increase the throughput. In this case, we can arrive up to 20 tons of material per hour, which is a lot. And we are processing at 2 meters per second. So again, this difficulty in acquiring all this massive data coming from the imaging sensor, and to analyze all this data very fast and give the order, and to open the valve in a specific moment to eject the material. So it's a really complex system, but it's now working. And the good thing is that the system can learn by itself. So we have developed algorithms, and when you try to separate, because the material is not always the same, because you can get material from different buildings, and this material can be different. So what we do is we use the material that is coming from a specific place. For instance, we introduce concrete, we introduce the ceramics or the gypsum or the bricks. So there is initial training. The machine is collecting spectra of this material, and then automatically generate a model that will be used for the effective separation of this kind of waste. You will see now a video in which we have implemented at our laboratory. This is again a vibrator to spread all the material onto the conveyor belt. We are taking the images very fast, processing them, and open and closing the electro valves that open and close the air of the ejectors. Okay, you can see that it's amazing how you can separate very fast the three different parts with a high degree of accuracy. And well, I think this is all from my side. You have here my contact, also the contact of my colleague, Jacobo Alvarez. And of course, if you have any question, I think after this presentation, there will be the time to do this. So thank you very much for your attention.
Thank you very much, Juan, for this very fascinating industrial point of view.
Mm-hmm.
So as we said, now we can have a short discussion if someone has some curiosity, some comments. I have a general curiosity by myself, especially I would say for Maxime and Anna, considering the development of the device and the computational tool. So how much the development are independent, or how much they should work closely together to keep the computational and the physical part together.
Well, for our point of view, it would be good if both tools were very dependent. Okay, because some of the objectives of our decision support tool is, well, to support the decision, because in the Sunrise we classify the different plasticizer in different categories depending on their physical properties. And well, our idea would be to work together with IREC in order to include some of this decision point to our tool, depending on the input data of the plasticizer.
Thank you. Are there questions or curiosities?
Yes, you heard me. I have a question. I'm Perrine Labor from AGC. I have a question regarding the sorting. Did you have already tried with different type of laminated glass to sort and to identify different group, like you say regarding the plasticizer, but maybe because there is some acoustic standard PVB, are you able to well sort this different type of PVB?
Okay, so yes, of course, we tried already different type of PVB. Of course, at the moment we are limited in some cases. In some cases, we can really easily identify the type of PVB, or if it's not a PVB, for sure, if it's like some ionopolymer, we can easily identify this. Or if it's in the case of PVB, we can identify different type of plasticizers that included in this PVB layer. So this is what we are doing. In case of acoustic or some solar PVB, we are still working on this, so it's becomes a bit more complicated. But yeah, it might be that combining different information from different sensors, we can do this. We can do this also this classification.
Okay, thank you.
Okay, so if there are no other questions, I just would like to remind you that so if you see my screen, next appointment at sunrise. So there are other webinars that we will do in autumn of this year about the use of the recycled polymer in textile and carpets. Then next year, the last two webinars in spring about the application of polymers in energy storage devices, and in autumn about the life cycle assessment of the wall process. And in any case, for all the news about the project, you can follow the Sunrise project. And so stay updated visiting the website, and thank you to everybody for participating to this meeting, and most of all thank to the three speakers of today for the very interesting presentations. And so I think we can close here the video call, and see you next time. Goodbye.
Thank you.
Thank you very much.
Bye.
Bye. Thank you.